watch the video.
Yeah, that's right. And I am making sure that the video is going now. I think on Friday when we were doing this, I got a little bit confused because some stuff happened at the last minute and it looked like the video did not go through.
Uh-oh.
So, yes, unfortunately we lost Friday's video, but at least the slides and everything are on. So, I hope everything's gonna go okay. My computer's been acting really weird, so it might crash out, but well, we'll see. Okay, so for today, I'll just make a few quick announcements. I do want to give a brief recap of a lot of the ring theory that we talked about on Friday. And then today I want to introduce a brand new idea that's going to get us into the real part of algebraic geometry, which is called the spectrum of a ring. And remember that really we're doing a lot of review of ring theory. And hopefully by Wednesday, we'll put everything together to explain what's happening. So Wednesday, I do want to spend time there discussing what's the definition of variety. So unfortunately, as I just said, Friday's lecture did not get recorded. I think something happened. I pressed pause at one point. I think pause because it never came back. It just stopped altogether, and I didn't realize that it just wasn't recording. So I'm sorry about that. Office hours are just the usual time, usual place. So 11 to 12, and then 4 to 5. If you can't make either one of those, just send me an email because I'm typically on Zoom most of the days today. And then, of course, the next homework assignment is going to be due this coming Friday. So this will be assignment number 6. And I did get all of the assignments from the 3 people who are currently signed in for the class for homework assignment number 5. So I'm going to try to grade that today and then hopefully have that back. All right, so hopefully you can hear me. It's my computer that crashed out again. So I'm going to...
We can hear you.
To bring the video back. Okay. And let's start my video. Okay, can you hear me just fine?
Yep.
Okay, all right, sorry about that. I'm just going to have to run this from my laptop then today. All right, so as a recap, remember that we spend most of the time on Friday going over rings. And simply put, a ring is a triple where R is a non-empty set. We have plus that we're going to call addition, and then we have times that we'll call multiplication. And essentially, we just have a list of 5 properties that we want to be true. And if we, in addition, say that we want a commutative ring, we'll throw in a 6th property that the multiplication here, the order really shouldn't matter. And the main thing to remember is that the integers is an example of a commutative ring. Right, so I would say they don't necessarily worry about a lot of these really weird, fancy definitions. There's only going to be a couple of standard examples we're going to play around with, and I'll try to go over those examples later on today. We'll say that we have a 0 divisor if there is a non-zero element A such that I can find a non-zero element B where the product is 0. A commutative ring without 0 divisors is called an integral domain. And again, the integers forms an example of an integral domain. So what I'll say is that I really just want you to think of the integers from here on out as kind of like a standard example of an integral domain. Really, everything we're going to try to do here for the course is going to focus on properties of integral domains. All right. Next, an element is said to be a unit if there's another element v, says that u times v is v times u is 1. So we'll put all of this together into one big set. We'll call this R star. So this is just the collection of units. And then finally, I want to introduce the idea of a polynomial ring. So polynomial is just formally a sum. We just have sums of powers of a variable where the coefficients that you have now have to lie inside of our ring R. And if the leading coefficient, this a sub n, does not equal to 0, so in this case, the a sub n will be this leading coefficient here, then we'll say that our polynomial has degree n, where n, of course, is the largest power of x that appears. If everything is 0, that is, if all of the coefficients are 0, so that we have here the 0 polynomial, we're simply going to say that the degree is negative infinity. Right, and I'll try to say why in just a minute, why we make this definition. So the collection of all such polynomials actually forms a ring with identity, but the main thing to remember is that here's the following result. if you start with an integral domain R, then the polynomial ring is also an integral domain. In fact, the degrees almost acts like a logarithm. So if you want the degree of a product of two polynomials, that is nothing more than the sum of the degrees. So this is kind of part of the reason why you want the degree of 0 to be negative infinity, is to make sure that this kind of logarithm function makes sense, right? So again, the degree of the product is the sum of the degrees. And finally, the units in a polynomial ring are very easy to compute. They will just be the units in the underlying ring R, right? So there's a lot that's very nice here whenever you're dealing with a polynomial ring over an integral domain. Next, we talked about the concept of a subring. So we'll say that a subset is a subring of R if it's closed under differences and closed under products, right? So what I mean by that is that the difference here is in S for all A and B in S, and the product here is in S for all A, B, and S. So I am not assuming that the element 1 lies in this set R, right? I'm just assuming that we have these two properties here. Next, we say that a well-defined map between two rings is a ring homomorphism if it preserves addition and if it preserves multiplication. Right, so just want to keep track of the fact that if I have a ring, there really are these three objects. There's the set, there's addition, there's multiplication. So well-defined map just means that it takes elements in one set to elements in another set. But then I also need to make sure that it preserves addition and it preserves multiplication, exactly in this way here. We'll say that we have a ring isomorphism if we have a bijective ring homomorphism. So this just simply means that it's a one-to-one correspondence. Right, so if I'm given an element in R, then that has to correspond uniquely to some element in S and vice versa. So on this slide, the main thing to remember is that if you're given a ring homomorphism, then there are two canonical examples of subrings. One is the kernel, which is a subset of R. Right, we'll define it in this way. It's a set of all elements that map to 0. That is a subring of R. And the image, which in this case here, is the set of all elements that look like they come from something in R. This is a subring of S. So again, we have two specific examples of a subring once we're given a ring homomorphism. And so the final thing we talked about was this idea of ideals. So I'll set it up in the following way. Say that we have a ring, and let's let I be a subring. So first of all, we can talk about cosets. So this is where we take a look at elements in the form A plus X, where X lies in the subring I. So as an example, we can let R here be the integers. We can let I be the collection of all even integers. That is a subring. And so if A here is equal to 0, then A plus I is just a set of even integers. But if A is equal to 1, then A plus I is just a set of odd integers. Right? So that's what we mean by cosets. They're just going to be elements in the form A plus I. Finally, we can put all of those together into one big set. So all of the A bars where A ranges over R, and this here is a set of sets. So again, if R here is the integers, I is the even integers, then R mod I just says it's a partition. I have either the odd integers or the even integers. So I kind of take R mod I and I kind of now have these two. So once we have a subring, then we have the following three equivalent statements. Let me only do this for proper subrings. Proper just means that I itself does not equal all of R. Of course, if I is equal to R, there's really nothing to do here. It's not really very interesting. So let's just say that I does not equal to R. Then we have the following three statements that are equivalent. So number one, I is the kernel of a ring homomorphism. That is equivalent to saying that we have the following two properties. Given any lowercase r and capital R, and any x and I, The product, r times x, is also an I. And of course, the order here doesn't matter. The product x times r is also an I. So if you will, think of r as like the integers, and I here could be the even integers. So if I take any even integer, and if I multiply that by an integer, then that again should be an even integer. Right? That's simply put what this says here. Finally, these two are equivalent to saying that R mod I is a ring with identity. So for example, again, if R is the integers and I is the even integers, R mod I would be the collection of evens and odds. And so in this case, it's simply a ring with two elements. Namely, I think of 0 bar as the even elements, and I think of 1 bar as the odd elements. Right, so again, these three here are equivalent. If I'm given a proper subring, then these statements here are equivalent. So I can use this now to make a definition. If any of these equivalent statements are true, then we'll say that R is an ideal, and then this ring, R mod I, is the quotient ring of R by I. Right, so again, I'm kind of using this here to motivate the definition of what do I mean by an ideal. You can take any of those three equivalent properties, does not matter. It's still what we mean by an ideal.
Sorry to interrupt. I have a question.
Sure.
So what's the difference between an ideal and just a proper subring?
This property here, I need to make sure that this here is happening with the products.
Yeah, okay.
Mm-hmm.
Yeah, but like property 3 is okay. So if I is just a subring,
Mm-hmm.
R over I might not be a ring. Is that?
That's exactly right. So it's hard to come up with a really good example because for the integers, it turns out that every subring is actually going to be an ideal. So you have to move to other rings to kind of get some of these weird properties to work out. So all that I can say is that for a lot of the rings that we're going to focus on, that this here is true. But you can actually come up with other rings where not every subring is an ideal.
Okay, thank you.
Mm-hmm. This is supposed to be akin to, like if you're dealing with group theory, is saying that not every subgroup is a normal subgroup. So this is the same thing here. What you really are trying to say is that you have a very specific type of subgroups. Like in this case, we have a very specific type of subring. Right. But again, most of what we're going to do here for this class, it doesn't really matter. A lot of the subrings are really going to be ideals, and they'll be very nice. Okay. All right. So for today, I want to remind you that our ultimate goal is to define a variety. And ultimately, we want to do this by using the ideals of a polynomial ring. So to this end, I want to spend some time reviewing ring theory. I want to talk about prime ideals, maximal ideals, polynomial rings, the isomorphism theorems. So I want to put everything together. And of course, to do all of this, I want to start with a few propositions to motivate some of the definitions that we're going to use today. But I do want you to remember that the ultimate goal is we're trying to expand our definition of what a curve is, of what a variety is. And we're going to do all of this specifically by looking at ideals in a polynomial ring. So we do have to focus on specific kinds of ideals and also what we mean by a polynomial ring. So to this end, let me start with a definition. Let's let R be a commutative ring. Then I claim that the following two statements are equivalent, given a proper ideal P. First, if we say that a product, or if we have a product A times B that is in our ideal, then either the first element is in the ideal or the second element is in the ideal. Right, so that's one of our properties. I claim that that is equivalent to saying that the quotient ring here is an integral domain. Right, so again, the quotient here is an integral domain, so that means that it doesn't have any zero divisors. That's equivalent to saying if the product A times B is in P, then either the first element A is in P or the second element B is in P. So remember, we're working in a commutative ring, so A times B is equal to B times A, right? So the order here doesn't matter. So I want to skim over the proof of this. This is kind of a standard statement that you would have in any class in ring theory. So this is, for example, something that you would have seen in 172, but I at least want to go over the proof here for those that maybe have not seen this before. So we'll do this in two directions. Let's first assume property I is true, right? So that is whenever A times B is in P, then either A is in P or B is in P. So let's assume that this here is the case. Well, P is a proper ideal. So according to the previous proposition, R mod P is a commutative ring. So really, I have to show that R mod P has no zero divisors. Right? That's what it means to be an integral domain. It's a commutative ring with no zero divisors. So let's just see what happens if we take the product. So let's say, for example, what if there were two elements so that the product here is 0? So remember, if I have a zero divisor, what that means is I can find two elements, A and B, both not 0, so the product is 0. That's what it means to be a zero divisor. Find two elements, both not 0, but the product is 0. So let's just ask the question, what if we have two elements so that the product is 0? But now this is 0 in the quotient ring in R mod P. Well, everything inside of the quotient ring really means the elements are happening in P. So whenever something is 0, at least 0 bar, that means that the element itself is actually in the ideal. Right? Remember that we had something like 0 bar is the even integers, 1 bar is the odd integers. It's similar to that idea there. So 0 bar just means it lies in P. So if A times B is 0 bar, then A times B has to lie in P. But we just got finished saying the property I is true, so either A is in P or B is in P. But if I go back to the idea of a quotient ring, if A is in P, then that means that A bar is 0 bar. And if B is in P, that means that B bar is 0 bar. So this here is just kind of winding through the definitions of what does it mean to be 0 bar? What does it mean to be an element of P? Okay, so any questions here on the first direction? All right, okay, let's move to the second direction. So now let's assume the second part, right? That the quotient here is an integral domain. So I need to prove the property 1 holds. So let's say maybe that the product here is in P. Well, then we can pass to the quotient ring. So this means that A bar times B bar is 0 bar in the quotient ring. But the quotient ring is an integral domain, so it has no zero divisors. So if the product is 0 bar, that means either the first one is 0 bar or the second one is 0 bar. Right? Because again, it has no zero divisors. There's no way I can have the product to be 0 unless either one of the two is 0. But as I just got finished saying, something being equal to 0 bar means that that element has to be in P. Right? Again, here we're just winding through the definitions of what's happening. So this shows that if R mod P is an integral domain, then here, if A times B is in P, then either A is in P or B is in P. So any questions here on this one? All right. So we'll use this here to make a definition. Any proper ideal satisfying either of these two equivalent statements is called a prime ideal. So you can use either definition that you want. Some books like to use this definition of I, that if the product here is in P, then one or the other is in P. Other books like to use the second property here, the R mod P is an integral domain. We're actually going to use this quite a bit today, that these two here are equivalent. So we'll define the spectrum of R as the collection of prime ideals. So we're going to take all of our prime ideals, put them all together into a set. And I want to point out that the zero ideal, so the ideal that just consists of one element, is a prime ideal if and only if R is an integral domain. right? So we are going to be using this quite a bit. Remember that we really care about the cases where R is an integral domain, and that's equivalent to saying that this trivial ideal, the ideal that just consists of the zero element, is itself a prime ideal, right? So this is the definition of a prime ideal. Now I want to figure out if I have two different rings, how are their prime ideals related? So say that we have two different integral domains, R and S, and let's focus on a non-zero ring homomorphism that we'll call phi. So because this is a non-zero homomorphism, one of the first properties we see is that the number 1 has to map to the number 1. Right? We have no choice. 1 has to go to 1. Number 2, let's look at what's called the preimage. So the preimage is the set of elements in R that map to this element phi of A that's in P, where P is, let's say, a prime ideal in S. So fix a prime ideal in S, and the statement is that phi inverse P is itself a prime ideal. So what we define now is actually a map on the spectra. So this says that we have a well-defined map on the spectrum of R and S that sends a prime P in S to a prime phi inverse P in R. So again, this is kind of a weird thing because here the directions are getting reversed. If I have a ring homomorphism that goes from R to S, I actually have a map that goes from spec S to spec R. So the arrows get reversed here, right? So any questions on this before we try to skim over the proof here?
Actually, I have a question.
Sure.
Can't we define a homomorphism from, can we define something from R to S that sends prime ideals in R to prime ideals in S?
The answer is simply put, not really, but I'll try to come back and say maybe an example about this a little bit later.
Okay.
Part of the issue is it's not clear how to define such a map. There are different ways to do it. It's just not clear how to do it. Right, yeah, I'll try to come back and maybe say a little bit more about it later. Yeah, but yeah, that's a good question. Right. So let me just try to skim over the proofs of these. Well, let's try to show the first one. So why is it that phi of 1 is equal to 1? Well, I know that phi of 1 is phi of 1 times 1, right? Because 1 equals to 1 times 1. So I can break it up like this here. So now let's take a look at this. Right, so I'm just going to subtract something from both sides and try to factor. So I need to ask a question. If the first one here is true, so say if one of these factors is 0, so if phi of 1 equals 1, then we're done. So let's say for the moment, what if phi of 1 does not equal to 1? Then that means, because again, we're in an integral domain, so we have no zero divisors. So this means that the first factor has to be 0. Right, so again, this here, phi of 1, has to be 0. But if this is the case, now pick any element lowercase r and capital R. Well, r is r times 1. So phi of r is phi of r times phi of 1, but then this is 0. And that contradicts where we were assuming that we have a non-zero homomorphism. So again, if phi of 1 does not equal to 1, then I would conclude that everything has to map to 0. And that's a contradiction. So we do have this very first case, that phi of 1 has to equal 1. Right? So let's go on to the second statement. So I want to prove that the preimage is a prime ideal. So to be a prime ideal, we need two properties. One is we need it to be a proper ideal. And the second one, we need this funny thing of if A times B is in the set, then either A or B is in the set. Right, so we need those two properties. So let's take a look at the first property. What if this preimage were not a proper ideal? Then we'd find, of course, well, the element number 1 is in R. So that means that the element number 1 has to be in this ideal phi inverse P. But you can kind of convince yourself that if the number 1 is in an ideal, then that means then the ideal has to be the entire ring. Right, so I'm kind of skimming over a couple of things here, but this is just saying that if phi inverse P is R, then the number 1 has to be in my ideal P, so then P here has to equal S, and that's a contradiction because I was assuming that P is prime, which means that P is proper. Right, so again, I'm kind of skimming over this for the sake of time, but it's just saying that if phi inverse P is not proper, then P itself is not proper, and that's a contradiction. Right? So now I need to move on to show that because we have a proper ideal, that this ideal has to be a prime ideal. So let's say for the moment that the product of two elements is in this ideal. Right? Let's say that A times B is in phi inverse P. Well, if I kind of wind through the definitions, remember, what does it mean to be phi inverse P? It really means that I have to take a look at the elements as that phi of A is in P. So this actually means that phi of A times phi of B is in P. But P is a prime ideal. So without loss of generality, I can say here that maybe phi of A is in P. But then that's equivalent to saying that A is in phi inverse P. So again, if the product is in phi inverse P in this ideal, then either A or B has to be in phi inverse P. But that's exactly what it means to be in prime. Okay, any questions on this one? Okay. All right, now we can do the third one, but the third one's a little bit silly because statement 3 follows directly from statement 2. So I just finished saying that if P is a prime ideal, phi inverse P is a prime ideal. So that's what it means to be a well-defined map. It just sends prime ideals to prime ideals. Right, so that's what this pullback does. It takes a prime ideal P to another prime ideal phi inverse P. Okay, so let's do one more proposition here. Now I proved that the following two are equivalent for a proper ideal M. Number one, there does not exist an ideal I that is strictly between M and R. Right, so again, I'm saying that I have an ideal M, that is a proper ideal, so M does not equal R. So I claim that there does not exist an ideal that is between M and R. That's equivalent to saying that R mod M is a field. Right, so I'm going to prove that these here are equivalent. Right, so let me just kind of skim over how this would go. Again, just for the sake of time. First, let's assume I, right, that there does not exist an ideal between M and R. Well, every field is a commutative ring. So we have this here. So I'm really going to take a look at the invertible elements. I really want to show that every non-zero element is invertible because that's what it means to be a field. Well, I'll pick an element that is non-zero. Let's call it A bar. And let I be the ideal generated by these two. Right, so if you will, you can think of this as I is the smallest ideal that contains M and contains the element A. That's really what I mean here. But I see that I contains M. Well, I just said that I is the ideal that contains M. And I does not equal M because I contains A, and A, by definition, is not in M. So I have an ideal that's a little bit larger. So this means that I has to be the entire ring. But to be the entire ring means that the element 1 is in the ring. And so if I just kind of stare at the definition of the way the ring is set up, then 1 has to be written in this way here. So if I look at what's happening mod M, then I see that A has to be invertible. Right, so again, I'm just going to skim over this for the sake of time. I really want to leave this for the slides for you to kind of read over just because we kind of started a little bit late today. But this is just quickly saying that if I have an element that is non-zero in the quotient ring, then here's its inverse. I explicitly just told you how to compute its inverse. And I'm happy to go over this in more details during office hours as well. So let me quickly go over the opposite direction. If R mod M is a field, let's say, by way of contradiction, that I can find an ideal I that is strictly between M and R. Right, so now we're going to try to do this by contradiction. Well, notice that the number 1 is not an I, because if it were, then I would have to equal R. So let's choose an element A that is in I, but it is not in M. Right, so again, I here doesn't equal M, so I can find an element in I that is not in M. So that really means in the quotient, A bar does not equal 0, because again, if it were 0, then A would have to be in M, so it is not 0. So that means it has to be invertible. Again, R mod M as a field means every non-zero element is invertible. So we can do this here. I can find this inverse. But now if I just simply wind through what's happening, then I can conclude that A times B actually was in I. Right? I'm not going to worry about doing this for the sake of time. And so then if I just kind of stare at a few of the properties, I would actually kind of rewrite things to conclude that the number 1 actually is in I. And that's a problem, because I just said a few minutes ago that 1 is not in I. So there's our contradiction. Kind of in some sense, because we have an inverse, then we do run into a couple of problems. Right, so again, for the sake of time, I'm not going to worry about the details here, but I'll say that if you do have questions, please come to office hours. Okay, so let me just try to recap what we just done here. Really, the proof isn't so important as it is the statement. Any proper ideal satisfying either of these equivalent statements is called a maximal ideal. So we'll put all of the maximal ideals into a set called max spec, M spec. And just to remind you, by field, what I really mean is every non-zero element is invertible. Right? That's kind of what we just worked out there in the proof. So it's a ring where every non-zero element is invertible. And so if I kind of stare at this for a minute, since F has to be a commutative ring with no zero divisors, it is an integral domain, which means every maximal ideal is an example of a proper ideal. So we actually conclude this. So if nothing else makes sense, I just want to point out that the set of maximal ideals is always contained in the set of prime ideals. Right, of course, this is as long as we're dealing with a integral domain R. Right? Okay, so let's kind of stop for a minute. Let's try to do some examples to kind of figure out what's going on here. Let's go back to our favorite integral domain of the integers. Right, so here we have z. Every ideal is in the form n times z for some integer n. And by n times z, what I simply mean is a set of integers that look like n times b for some b. So these are just the multiples of n. Right? That's what every ideal of z looks like. They're just multiples of n. In fact, this ideal is a prime ideal if and only if either n is 0 or n itself is a rational prime. N itself is a prime number. So this tells me now what all of the prime ideals of z look like. On the other hand, if I look here at the quotient, R mod I, that is simply this ring z mod nz. And so I see that this is a maximal ideal if and only if n itself is a prime number. That's because in this case, z mod nz is the finite field of p elements. So again, I is a maximal ideal if and only if n is a prime number. So then we're able to conclude the following. Spec of z looks like 0 along with the prime numbers, because once I pick a number n, either n is 0 or n is the prime, I can then work backwards to generate a prime ideal. Right? On the other hand, M spec only looks like the prime numbers. Because if I'm given a prime number here, then again, I can generate a maximal ideal, right? P times Z. So you'll notice that 0 is contained because Z here is an integral domain. You'll also notice that M spec is a subset of spec because every maximal ideal is a prime ideal, but there is a prime ideal that is not a maximal ideal, namely 0. All right, so these should be kind of the things to take away here on this slide in terms of maximal ideals versus prime ideals. So every maximal ideal is prime, but not every prime is maximal. So we'll come back and we'll talk about that more as well. As another example, let's consider a field F, and then let's take this integral domain R, which is the polynomial ring over F. So remember that every field is an integral domain, and if you're given an integral domain, then the polynomial ring is also an integral domain. Right, so we start with the field F, then f of x is also an integral domain. In fact, if you're working with the field, the only proper ideal in a field is the 0 ideal. Right, so this is the only proper ideal. And so in this case, and actually, sorry, this is a typo here on the slide, spec of f is equal to just this one ideal. And it turns out that M spec is also the same thing. So I wrote here the empty set. This is actually wrong. The empty set should also be the 0 ideal here. So in this case, spec F and M spec F are actually equal to each other. Right? So if you're dealing with the field, spec F and M spec F are actually going to be equal because they only consist of one element, namely the 0 ideal. On the other hand, let's take a look at the following surjective map. So here, I'll take anything I want in spec R, and I'm going to send that to the 0 ideal. Right, so just the silly map that says take any prime ideal of R, send that to the 0 ideal of F. So this is the surjective map. I don't care anything about spec R. I don't care how many elements it has, I can still do this. The reason this always works is that this comes from the following inclusion. So I have an inclusion map that sends an element A of F to this constant polynomial. So here I have a ring homomorphism that sends a field into the polynomial ring. And according to the theorem, now I've reversed the arrows, and that corresponds to spec R going into spec F. Now, there was a question earlier about, can I kind of reverse the arrows here? So for example, if I have a map going from F into R, can I use that to write down a map maybe going from spec F into spec R? Well, the problem is that there are a lot of ways to do that. So I'm not going to worry about saying that here because we're already kind of over time. Maybe I'll go ahead and put that here in the notes, then we can talk about that a little bit more later. But again, this just simply says that there's kind of a nice way to go from spec R to spec F as long as F is contained in R, but there is really not a nice way to go from spec F into spec R because there's many, many different ways to do this. And again, I'll try to say a little bit more about this. I'm going to kind of put this here in the notes. Right. So any questions here before we call it a day? Okay. All right, so I've only made it through about half the lecture here. So I'm going to try to play around with the lecture notes that are online and move things around. But on Wednesday then, I do want to spend some time going over the isomorphism theorems to explain how we're going to use that to formally define what do we mean by variety. All right. Okay, well, you all have a good rest of the day and try to see each other on Wednesday then.
Have a nice day.
Have a nice day. See you.
All right, thanks. You too.
Have a nice day. Thank you.
All right, you're welcome.